All right, we're back, section 7.2. This, I promised, would build on section 7.1. 7.1 was exposing you to the fundamental trig identities and how to manipulate with them. 7.2 is verifying trig identities. So in these problems, these are basically like mini proofs. And I know that word makes all of you jump and scream with enthusiasm and joy as much as I scream when I hear that word. I promise these proofs, in quotation marks, aren't like, they're not bad. They're actually really interesting. And if you enjoyed section 7.1, 7.2 just builds on it. In actuality, I think 7.2 is easier than 7.1. 7.1, we didn't really know what we were working toward. We just knew that we were trying to simplify these expressions. Now we're given some expression equals some other expression. And our only goal is to use our identities to make both sides equal each other. So if we look here, there's a lot of techniques that we can employ that are the same. First, and this is true of any proof, we're going to work with one side of the equation at a time. Okay? Usually we're going to start with a more complicated side. And we're going to look for opportunities where we can factor, add or subtract fractions together, difference of squares, or actually distribute, square the binomial. We're going to look for denominators, like we did last section, that we recognize are factors of the Pythagorean identities. We're going to look for opportunities to use those identities. Where are the squared terms? Let's look at Pythagorean. Let's look at the quotient identity. Let's change things to sine and cosine if all else fails. You also probably want to check this time, since we know what we're working toward, what are we working toward? What expressions are in there? How can I take the expressions that I'm starting with and use the identities to turn them into what I want to end with? And truly, in the end, just try something. I promise, even if you end up with some completely insane expression in the end, it was still worth something. It still taught you something and shows you some glimpse of what you should be doing when you're working toward your ultimate goal. So we're still using these same identities. One key point that I want to make here is that, and let's take a look at example 1. Okay, so I'm given an expression equals another expression. That equal sign is a little deceptive. When I'm verifying these identities, you have to keep in mind that I'm trying to prove that equal sign. I can't take for granted that this is an actual equality. What that means is that I can't do things that I can do when I know that two things are equal. I can't cross multiply. I can't add or subtract things to both sides of the equation. I can't move one term to the other side. Those are only things I can do when I know I have an equality. And here, that's what I'm proving. So I can't just assume that. Otherwise, why am I proving anything? So with that in mind, let's start example 1. For these proofs, and again, I'm using that term even though I know that most of you won't like that, because these are mini proofs. For these proofs, I want you to use 2-column proofs. So here's what I mean. On each side, in each column, write one side of this equality that we're trying to prove. So in this case, secant squared minus 1 over secant squared equals sine squared. And you're going to rewrite both sides of the equation for each step. Yes, I know many of you are going to roll your eyes and say, good God, why do I have to do this? I can just see it. Why do I have to show all this work? It's more work for me. I'm tired. I'm lazy. Guess what? I don't care. I want to see all of your reasoning. I want you to get in the habit of being incredibly rigorous and formal with your reasoning. Because that is, after all, one of the main things I'm trying to teach you in a math class. You need to be able to go step by step through what you did. I have to be able to do that to grade you. So please, make my life easier when I'm grading you. It puts me in a better mood when I'm grading. Hint, hint. So rewrite for each step. And then secondly, we're only going to change one side of the equation at a time. I don't want you to work both sides of this equation at the same time. I will let you work both sides separately. I just don't want you to go from one step to the next step and have changed both sides completely, because that makes it harder for us to follow along. Okay? Make this simpler and easier to follow. So here, for this proof, the left side is more complicated, so I'm going to try to simplify that. I'm looking at those secant squareds, and immediately I'm thinking Pythagorean. I know that 1 plus tangent squared equals secant squared. In other words, secant squared minus 1 equals tangent squared. So I'm going to take that numerator there and rewrite it as tangent squared over secant squared equals sine squared. Now I see tangent and secant. I know that what I'm working toward is just a sine squared. So I'm going to rewrite tangent and secant in terms of sines and cosines. So tangent is sine squared, well, tangent squared is sine squared over cosine squared. And then secant squared is 1 over cosine squared equals sine squared. I'm dividing two fractions. When I divide by a fraction, that's the same as multiplying by the reciprocal of the fraction. And cosine squared cancels out. So in the end, I have sine squared of theta equals sine squared of theta. And I'm done. Beautiful. Isn't that fun? That was so fun to me. Anyway, that's how I want you to do all of these proofs. Exactly like that. 2 columns, 1 step at a time, 1 side at a time, rewriting both sides every time. All right, example 2. What are we thinking? 1 minus sine theta, or actually not theta, I'm sorry. If you don't recognize that symbol, it is the Greek letter alpha. It's lowercase alpha. You'll notice that looks a lot like our lowercase a. It's not coincidental. 1 minus sine alpha and 1 plus sine alpha are my denominators. I'm going to add these two fractions. And so to add these two fractions, I know that I will need common denominators. And to get common denominators, I'm going to need to multiply the other fraction by that denominator. So 1 plus sine alpha over 1 plus sine alpha. Then over here, I'll need to multiply by 1 minus sine alpha over 1 minus sine alpha. And then simplify 1 plus sine alpha. I'll have the same denominator. 1 minus sine alpha times 1 plus sine alpha. I know that that will turn into 1 minus sine squared alpha when I distribute those, plus 1 minus sine alpha. Okay. 1 minus sine alpha is cosine squared. That's the Pythagorean identity. And then in the numerator, I have plus sine alpha minus sine alpha. That cancels. 1 plus 1 is 2. Whoops. Sorry about that. And if I rewrite this, just for clarity, then you see 1 over cosine squared alpha, which we know is secant squared alpha. So I'm going to continue up here, sorry. 2 secant squared alpha equals 2 secant squared alpha. And we're done. Again, it's just so nice. I love this. And our proof is nice and organized, step by step. Now, if you see other ways of verifying these identities, by all means. There's not always just one right answer. In fact, in math, there are often many right answers or right ways to get the right answer. As long as you end up proving that both sides are the same, there's a lot of ways you can go about these problems. So if you saw a different method, by all means, try it. It doesn't mean you're wrong. Let's look at example 3. Verify the identity. This looks like it's going to be a long one. Tangent squared x plus 1 times cosine squared x minus 1 equals negative tangent squared x. All right, now here I notice that I'm looking to end up with tangent, or in this case negative tangent squared. So I don't want to rewrite tangent squared in terms of sine and cosine. I want to leave it there, and I'm just going to multiply these two binomials together. So we're going to distribute these, square them, or not square them, you know what I mean. So tangent squared times cosine squared, box method. There's the word I'm looking for. I didn't learn how to multiply using box method, so I think it's fantastic that you guys have that great method to use. If you do box method for these, you will end up with an expression just like that. Okay? And now I see this minus tangent squared, and I know that's what I want to end up with. So I'm going to leave that there. I'm not going to change that. However, I see this tangent squared over here, and I am going to change that, just so that I can keep trying to simplify. So this tangent squared turns into sine squared over cosine squared times cosine squared plus cosine squared minus tangent squared minus 1 equals negative tangent squared x. Cosine squared cancels here, because that denominator was 1. And so I'll end up with sine squared plus cosine squared minus tangent squared minus 1 equals negative tangent squared x. Pythagorean, I'm going to scream that. I should turn that into like the movie Up when Doug shouts squirrel. Maybe I'll just shout Pythagorean anytime I see sine squared plus cosine squared or secant squared minus 1. So sine squared plus cosine squared, Pythagorean, that's 1. One minus 1 is 0. And I end up with negative tangent squared equals negative tangent squared. And I'm done. Oh, that's so nice. Let's keep going. All right, these are just so fun. Like people buy books of Sudoku puzzles. I would honestly buy a book of verifying trig identities and do that in my free time. I mean, you already think I'm weird, so I have no problem telling you that. Example 4, verify this identity. I don't know why I keep writing or reading the instructions. Of course, it's going to say verify the identity. So that's all we're doing in this section. All right. Now, which side looks more complicated here? I'm going to say that the left side is because I'm adding. The right side is multiplying, it's just one term. Left side is two separate terms. So I'm going to try to simplify the left side and see what I get. I see tangent and cotangent, so I'm going to change to sines and cosines. Sine x over cosine x plus cosine x over sine x equals secant times cosecant. I'm going to get a common denominator, so I'll need to multiply by sine x over sine x. And then here I need to multiply by cosine x over cosine x. So my new denominator will be sine of x times cosine of x. Sine times sine is sine squared. Cosine times cosine is cosine squared. Pythagorean, that's 1. And now, just for clarity, I'm going to rewrite this separately, and that's okay. I'm multiplying. I didn't actually change anything. 1 over cosine is secant. 1 over sine is cosecant. And I'm done. That's so simple. I do hope you're enjoying this, truly. Example 5. Gosh, both sides look kind of complex. I'm going to work the left side. I don't really have an exact reason for why I'm choosing to work the left side instead of the right. I just think it's easier to turn something into an expression with sines and cosines than it is to take an expression with sines and cosines and then turn it into an expression with secant, cosecant, tangent, cotangent. So I guess that's why I'm doing this. So on the left, I'm going to change using reciprocal and quotient identities, respectively, to that. And I have that same denominator, so I'm just going to add those fractions. 1 plus sine y over cosine y equals cosine y over 1 minus sine y. Here's where things get a little tricky. I know that on the right, I want a denominator of 1 minus sine y. And so on the left, I don't have that denominator. How can I make that denominator appear? I could just multiply by 1 minus sine y. But then I'd have to do that to the numerator also. So if I simplify that, I have 1 minus sine y times 1 plus sine y. Hey, those are the factors of the Pythagorean identity. So that's 1 minus sine squared y over 1 minus sine y times cosine y. So I'm getting there, right? I at least have that term in the denominator. 1 minus sine squared, Pythagorean, is cosine squared over 1 minus sine y cosine y. And hey, cosine's going to cancel. I'm going to continue up here. Whoops. Didn't mean for that to happen. Cosine cancels. So cosine over 1 minus sine. Beautiful. Two sides are equal. All right. Last example. So just like 7.1, I'm going through all these examples for you, but really the best way to get comfortable with this is just to do them. So I hope you're reviewing this just to follow along with my thinking and what I'm looking for, but that you're going back to the practice problems and trying them yourself, because that's really the only way you're going to get good at this. So verify this identity. I'm going to leave space for another column if I need it. Cotangent squared over 1 plus cosecant squared, or not squared, sorry, equals 1 minus sine over sine. I'm going to work the left as a squared term, cotangent, cosecant. I don't like it at all. So let's rewrite everything in terms of sine and cosine. I'm going to add the fractions in the denominator on the left. So that means I will need a denominator of sine. So I'm going to multiply by sine over sine. And I'll get my common denominator was sine. Sine plus 1. And now, this is tricky. Everything else is in terms of sine, except that cosine squared. So I'm going to change cosine squared to be in terms of sine. And I know, but Pythagorean identity, that's 1 minus sine squared. Okay? And I know that 1 minus sine squared factors so much to write. But I do expect you to write it. And now on the left, I'm dividing by a fraction. I'm dividing a fraction by another fraction. That's the same as multiplying by the reciprocal. Well, sine of theta plus 1 and 1 plus sine of theta, those are the same. And sine will cancel with one of the sines in sine squared. And so I ended up with 1 minus sine theta over sine theta equals 1 minus sine theta over sine theta. Amazing. So that's it. Okay, that's really it. Go back, practice, please. Come talk to me if you still just don't understand what I'm doing or why I'm doing it. Or you're really uncomfortable with the algebra that I'm doing, adding and subtracting fractions, especially factoring, things like that. So please come talk to me. I'd love to help you. Truly, I just love this concept so much. So I want to help you, and I want you to love it too. So bring your questions to me. Otherwise, do some practice, and I'll see you next section. Thank you so much.